The majority of today's unmanned ground vehicles are teleoperated, doing what and only what the warfighter directs them to do. While such systems save lives, lack of onboard intelligence limits the range of possible missions and can put operators in harm's way. The Space and Naval Warfare Systems Center, San Diego, has been a pioneer in robotics since early work in unmanned undersea vehicles in the 1960s. The Ground Robotics program, initiated in 1982, produced a series of teleoperated vehicles performing recon and surveillance for the U.S. Marine Corps, expanding into autonomous security robots for the Army in 1990. The center began supporting unmanned surface vehicles for the Navy in 1999 and later established a focused effort to enhance the autonomy of man-portable systems used in explosive ordnance disposal.
This is a conventional iRobot PackBot chassis, which we've modified with a couple of payloads under the CCAP program, which provide a lot of additional capability. One of the most important capabilities is the ability to sense things in the environment, and we do this for obstacle avoidance, mapping, and localizing the robot. The most obvious one here is a laser, which lets us measure the distance in a 360-degree range around the robot very accurately. We also have a stereo sensor, which lets us do the same thing with a little bit less range, but it also is a three-dimensional sensor, so we get a much fuller representation than just the laser alone would give you.
This new technology has been incorporated in the Autonomous Robotic Mapping System, or ARMS, scheduled for initial user evaluation in 2008. ARMS automates the risky and labor-intensive task of exploration in unknown or hostile environments while providing extremely accurate maps of the structure. The augmented virtuality representation shown here is based upon the Idaho National Laboratory's 3D interface. This map shows walls and rooms with far greater accuracy than a hand-drawn map. Detected openings on the right side of this hallway, for example, are marked with doorway icons for later reference. The term semi-proximal implies that the human and the robot are going to work together as a team now that the threat is known in advance. The robot will accompany the warfighter back into the area of interest, helping to protect him en route. In support of the warfighter's associate concept, the robot currently has 5 different sensor modalities that allow it to keep track of its partner's location. Here we see a following behavior, supported only by the onboard laser. Similar performance is obtained using a vision-based technique. Such sensor redundancy is necessary to ensure reliable performance under dynamic real-world conditions. In this Paradigm 6 scenario, the robot infers what it should do based on its perception of what the human partner is doing and what the threat is in the surrounding environment. When the warfighter flips off the weapon safety, for example, the robot shifts its visual attention from following its partner to searching for a potential threat. If the warfighter begins firing his weapon, the robot can automatically execute supportive behaviors to shield its partner and/or distract the enemy. The robot returns to follow mode when the weapon is made safe, then automatically initiates another shielding maneuver as the warfighter engages a new threat. Developed by SAIC Englewood, the instrumented airsoft M4 machine gun serves as a laboratory surrogate for similar hardware pursued by the Army's Future Force Warrior program. The Unmanned Systems branch already has extensive experience in the development of automated target acquisition and tracking systems for non-lethal weapons. Obvious synergy can now be realized by merging this advanced fire control software with proximal human-robot interaction behaviors. Here, the robot's weapon automatically follows that of the human partner, allowing its target acquisition system to precisely lock on and track any perceived threat, firing only if commanded by the warfighter.